Welcome to this concept explainer, brought to you by CBSE ScoreLab of ProfSam.com. That is ProfSam.com. We are starting a foundational deep dive today into Unit 14, Semiconductor Electronics. Specifically, we are tackling the very first hurdle, the fundamental classification of solids into metals, semiconductors, and insulators. We will not just learn the definitions. We're going to understand the why behind them.
Right. This unit feels like the bridge between, classical physics and modern electronics. So getting the base correct, understanding why different materials behave so differently, that seems absolutely essential.
Exactly. And let's start with a question that puzzled scientists for years. It immediately shows why we need this energy band theory. We all know the copper wire in our fan is a brilliant conductor, and the plastic on the outside is a perfect insulator. Simple.
That's straightforward.
Now, consider two materials made entirely of the exact same element. Carbon. We have diamond, which is, famous as a perfect non-conducting insulator. And then we have graphite, which we use in pencils and batteries because it is actually a surprisingly good electrical conductor.
Wait, what? I didn't know that graphite was a good conductor, but diamond is an insulator. That feels genuinely counterintuitive. How can the same basic building block, carbon, give you two materials with completely opposite electrical properties? It just defies simple logic.
It does. It really does. And that profound difference, the reason why diamond blocks current and graphite allows it, that sits at the very core of our deep dive today. The secret, as Source 2 tells us, is entirely in the material's internal atomic arrangement. The core idea basically is this. Electrical conductivity is simply the result of electron mobility.
How free they are to move around.
Exactly. How free they are. We're just asking one question. How tightly are the electrons bound to their parent atoms, and how much energy do they need to be set free?
So we can't just look at the element. We have to look at the element structure. But why do we need this whole complicated band model to explain something as simple as electrical flow?
That's where the physics gets really interesting. To explain why this happens, especially in solids where you have billions of atoms packed so closely, we need the energy band model. Think about it. When a single atom is alone, its energy levels are sharp and distinct.
Okay.
But when you bring billions of them together, their energy levels start influencing each other. Because of the Pauli exclusion principle, which says no two electrons can have the exact same quantum state, these discrete levels, they have to spread out a little. They create these continuous, wide regions of allowed energy. And these regions are what we call energy bands.
Okay. So step one is that the atoms crowd together. And because they're so crowded, the energy levels sort of blur into these wider bands. That makes it less abstract.
Precisely. Now, let's use our primary analogy to visualize this. The stadium seating model. Think of all the available energy levels for electrons as seats in a huge stadium, arranged in two main sections. The lower section, which holds all the electrons involved in covalent bonding, these are the fixed occupied seats. This is the valence band.
So these electrons are bound, they're stuck in their seats?
Stuck in their seats, exactly. They are not moving, so they cannot carry any current. Now, immediately above this is the upper section, which is usually empty. This is the conduction band. For an electron to be free to roam and carry current, it must reach this upper level. It's like being allowed to walk around in the aisles.
So current flow is all about getting electrons from the filled lower band, the valence band, to the empty upper band, the conduction band.
Correct. And the entire difference between a metal, an insulator, and a semiconductor is the empty space, the energy height between these two sections. This space is called the band gap. We denote it as A Galler.
The band gap.
Yeah. Now, in a metal, those two sections, the valence band and the conduction band, they are completely overlapping.
Overlapping.
Yes, the electrons are already sitting in the aisles, you could say. The band gap, A edge is 0, they move freely with even the slightest encouragement. But in an insulator, the gap is immense. The two bands are separated by a chasm, often greater than 5 electron volts, or EV.
That sounds like a lot.
It's a huge jump. No matter how much reasonable heat or voltage we apply, the electrons just cannot make that massive energy jump.
And the semiconductor must be the compromise then, right? The gap is moderate, somewhere in between.
Exactly. Somewhere between, say, 0.7 EV and 3 EV. It is a manageable jump. You just give those electrons a moderate thermal kick like just having the material at room temperature, and some of them will have enough energy to hop the gap and become free carriers.
Wait, I have one doubt here. If this gap is energy, why do we measure it in electron volts and not, say, a physical distance like nanometers? This is a very common point of confusion for students.
That is the #1 silent killer misconception, actually, and it is so important you ask this. You must remember that the band gap is not a physical distance between atoms. It is an energy difference.
The energy difference, yeah.
Yes. 1 electron volt, or 1 eV, is simply the energy an electron gains when you accelerate it through a potential difference of 1 volt. It is literally the tiny punch of energy needed to kick that electron up from its bound state in the valence band into the free-roaming state in the conduction band.
And that energy can come from heat.
It can come from heat, from a photon of light, or from an applied voltage, any of those. Okay, so now that we have the band structure visualized, let's see how NSERT formally defines these materials. Let's start with their measurable ability to carry current conductivity and resistivity. Could you read out the classification based on electrical conductivity for us? Just summarize the relative values.
Certainly. Based on conductivity, which is sigma, and resistivity, solids are classified. First, metals. They have very low resistivity, typically ranging from $10 down to $10 a meter, which means their conductivity is incredibly high, 10 to 10 Siemens per meter. They're at one extreme.
Right, the best conductors.
Then insulators are at the complete opposite extreme. They have extremely high resistivity, sometimes up to 10, 19 a meter, and so their conductivity is negligible.
Almost zero.
And finally, semiconductors are in the intermediate range. Their resistivity is much better than insulators, spanning about 10 to 5 to 10 centimeter, putting them exactly between the metals and the insulators.
Perfect. And just notice the scale of that difference. We are talking about differences spanning over 20 orders of magnitude. It's a massive range. And it all comes down to that tiny, invisible energy gap. Let's also cement the formal definitions of the bands now. The valence band contains the energy levels of valence electrons which participate in the bonding. The conduction band is the energy band immediately above it. And SOR is the energy separation between the top of the valence band, which we call EV-Eller, and the bottom of the conduction band, EC-Eller. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is PROFSAM.com. Let's move on to a practical example that really highlights why the band gap size is everything. Consider silicon, Si, and germanium, J. Both are intrinsic semiconductors. Now, silicon has a band gap, AGellers, of about 1.1 eV, while germanium has a smaller gap of about 0.67 eV at room temperature.
So, because germanium's gap is smaller, it should be a naturally better conductor than silicon, correct?
That's absolutely correct. From a purely electronic perspective, yes. Because Ben has a smaller A-dollar, the thermal energy available at just room temperature can cause exponentially more electrons to jump into the conduction band than in silicon.
Less effort for a bigger return.
Exactly. This also confirms why pure carbon in its diamond form is useless for electronics. With a massive 5.4 eV gap, the energy at room temperature can't do anything.
The jump is just too huge.
Too huge. The material remains a perfect insulator.
But wait, if germanium is naturally more conductive, why is silicon used in almost all integrated circuits today? I thought manufacturers would prefer the better conductor.
That is a great deep dive question, and it moves beyond the basic definitions. While J is more conductive intrinsically, silicon won the manufacturing race for two critical reasons. First, silicon is one of the most abundant elements on Earth, so it's incredibly cheap.
Okay, that makes sense.
And second, and this is more important, silicon is far more stable at higher operating temperatures.
Thermal stability.
Yes. If a device heats up, the smaller 0.67 eV gap of germanium starts producing too many free carriers. It starts behaving like a metal, and the device fails. Silicon's wider 1.1 eV gap gives it better thermal tolerance, which is essential for stable, modern electronics. And this brings us right to the next topic, controlling this conductivity. Since pure silicon is a poor conductor, we have to artificially introduce impurities, which is the entire subject of doping and creating extrinsic semiconductors. Okay, time for the silent killers. The concepts that seem logical but trick you in exams and cost you marks. We have two big ones.
The common traps.
Yes. Misconception number 1. The idea that at absolute 0 Kelvin, all electrical activity just stops and no material can conduct electricity.
I can see why a student would think that. At 0 Kelvin, there's no thermal energy, so everything is frozen. No movement.
And that part is true for semiconductors. At 0 K, they behave exactly like perfect insulators. There is zero thermal energy to help electrons cross even that moderate band gap.
Right.
But the killer correction is this. Metals still conduct. And often they conduct even better.
Even with no heat. Why?
Because the conduction band already overlaps the valence band. The electrons are already free to move, independent of thermal energy. No thermal kick is needed to start the current flowing.
Okay, so metals already have the bridge built. Semiconductors have to wait for the heat elevator to arrive.
Yep.
That is a very clear distinction.
Exactly. Now, misconception 2 relates to how heat affects resistance. Students learn correctly that heating a metal increases its resistance, and they often assume the same for semiconductors.
But when you heat a metal, the atoms vibrate more, right?
Yeah.
That lattice vibration just gets in the way of the current, slowing the electrons down. Why would a semiconductor be different?
It's because the dual effect of heat on a semiconductor. In a metal, increasing temperature only causes more obstruction. That's it. But in a semiconductor, increasing temperature does 2 things. Yes, it causes a slight increase in obstruction, but it also provides enough energy to break exponentially more covalent bonds.
So it's creating new charge carriers.
A huge rush of newly freed charge carriers, both electrons and holes, and this enormous increase in mobile carriers easily beats out the slight slowdown caused by the shaking atoms. The net result is this, and you must remember the rule. For semiconductors, hotter, more conductive.
Wow. So the exponential generation of new carriers completely dominates the small increase in resistance. Heat unlocks electrons in semiconductors, which is the opposite of what it does to a metal. That's a crucial difference to memorize.
It is. Now, for a memory anchor to help you lock this relationship in place, let's use the mnemonic MAGIC.
Magic, okay.
M stands for metal, the bands merge, meaning AGO is 0.
M for merge.
Got it. A stands for always. Metals always conduct even at 0 Kelvin.
A for always.
G stands for gap. The gap size is what dictates the material type.
Okay.
I stands for insulator, an immense gap where A Gers is greater than 5 eV. And finally, C stands for compromise. The semiconductor is the compromise, having that moderate, tunable gap that lets us control its conductivity. To reinforce this, try this simple physical gesture. Use your hands to show the 3 structures, hands completely overlapping for the metal.
Okay, like this.
Hands stretched far, far apart for the insulator, and hands held just close together, showing a small jump for the semiconductor. Remember the phrase, metals overlap, insulators separate, semiconductors compromise.
That's a good one. Metals overlap, insulators separate, semiconductors compromise.
Let's consolidate the 3 essential exam-safe points regarding the classification of solids before we wrap up. First, solids are fundamentally classified based on their electrical resistivity and conductivity values. Metals have resistivity that is 20 orders of magnitude lower than insulators, with semiconductors in that useful, controllable range in between.
Right, the numbers.
Second, this measurable difference arises entirely from the energy band gap between the valence and the conduction band. Metals have A-Gillers of basically 0, insulators have a very large A-Giller, and semiconductors have a moderate A-Giller that can be breached by thermal energy.
So it's all about the gap.
It's all about the gap. And third, semiconductors exhibit unique temperature-dependent conductivity. Unlike metals, where heating increases resistance, thermal energy in semiconductors excites new carriers across the gap, causing their conductivity to increase sharply when heated. To gain mastery over these concepts and get maximum marks in 12th CBSE Physics, Chemistry, and Maths, visit ProfSam.com.
That is PROFSAM, right?
Yes, PROFSAM.com.
Thank you for joining us for this deep dive into the foundational concepts of semiconductor electronics. We hope you now understand why a diamond and a pencil tip can be made of the very same element, yet have such vastly different fates in an electric circuit.